6 kilometers beneath this ship, Japan has connected a mining system to a mineral deposit. What came back was not gold, oil, or solid rock. It was mud. But the real prize is leverage. The mud contains metals used in motors, robots, wind turbines, aircraft, and guided weapons. China controls 91% of refining for key magnet rare earths, and 94% of the permanent magnets made from them. On February 1, 2026, Japan confirmed that rare earth-rich sediment had reached the deck from roughly 6,000 meters below the Pacific. It was the first such recovery from this depth. Japan has proved one impossible-looking step. It has not yet solved the three that decide whether China should worry: scale, processing, and price. Rare earths are 17 elements with names like neodymium, praseodymium, dysprosium, and terbium. Most people never see them, yet they sit inside some of the world's most valuable machines. Neodymium and praseodymium create powerful permanent magnets. Dysprosium and terbium help those magnets survive intense heat. Together, they make smaller, lighter motors possible in electric vehicles, industrial robots, drones, aircraft, and military systems. The strategic problem is not simply where the elements are mined. In 2024, China produced about 60% of the world's mined magnet rare earths. Its share rose to 91% for refining and 94% for sintered permanent magnets. Opening another mine, therefore, does not create another supply chain. The material must be concentrated, chemically separated, converted into metals and alloys, and manufactured into magnets. China built scale and expertise across every stage. That is where the real monopoly lives. Permanent magnets are a small part of an electric car's cost. Remove them, and the motor may not exist. A tiny interruption upstream can stop billions of dollars in production. That warning became real in April 2025, when China introduced export controls covering 7 heavy rare earth elements, related compounds, and some magnets. Export volumes fell sharply in April and May. Manufacturers struggled to secure material, while automakers reduced utilization or temporarily stopped production. The disruption did not need to last forever. It only needed to prove that access could be slowed, licensed, or redirected during a political crisis. For Japan, this was the return of a lesson it had learned 15 years earlier. In 2010, Chinese export restrictions exposed how vulnerable Japanese industry had become. Roughly 85% of Japan's rare earth imports came from China. Tokyo responded with recycling, lower material magnets, investment in alternative suppliers, and a challenge through the World Trade Organization. By 2020, China's share of Japanese rare earth imports had fallen to 58%. But that progress concealed a dangerous detail. Japan's 2026 manufacturing white paper said imports of heavy rare earth elements were still 100% dependent on China. Japan had diversified the easier market, but heat-resistant magnets remained hard to replace. That weakness pushed the country somewhere almost no mining company would choose to begin. Minamitorishima sits 1,950 kilometers southeast of Tokyo. It is a tiny Japanese island surrounded by open Pacific. Its importance is not the land, but the exclusive economic zone around it. In 2013, researchers reported exceptionally rich rare earth mud at depths approaching 6 kilometers. 5 years later, they modeled 2,500 square kilometers, roughly the size of Luxembourg. Their estimate? More than 16 million tons of rare earth oxides. That number needs an important label. It is a model-based resource estimate, not a proven reserve. It does not mean that all of the material can be recovered, or that recovery will make economic sense. Still, the most promising 105 square kilometer zone was estimated at 1.2 million tons. The problem was no longer finding material. It was operating an industrial system beneath 6 kilometers of moving ocean. Rare earths are not evenly mixed through this mud. Much of the content sits in coarse calcium phosphate grains, formed partly from microscopic marine remains. That unusual structure may become Japan's first advantage. Larger, richer grains can be separated from finer, lower-value mud. Researchers tested a hydrocyclone, a machine that spins slurry and sorts particles using centrifugal force. Laboratory tests on Minamitorishima samples recovered roughly 71 to 93% of the rare earths. In the richest case, the process raised the grade to about 2.6 times the original slurry, while reducing its retained volume below 1/5. Think of it as removing most of the worthless luggage before a 6-kilometer elevator ride. It does not prove profitability. But at this depth, every ton that does not need to travel upward saves energy, equipment capacity, and money. Chikyu, one of the world's largest scientific drilling vessels, was selected for the test. It is 210 meters long, with a gross tonnage of 56,752 and a 70-meter derrick. 6 azimuth thrusters, each rated at 4.2 megawatts, allow its dynamic positioning system to resist wind, waves, and currents. That precision matters because the connection extends farther vertically than the height of Mount Kilimanjaro. Chikyu reached the Minamitorishima test area on January 17, 2026. The first recovery operation began on January 30th. In the early hours of February 1st, the team confirmed that rare earth-rich mud had reached the ship. From the deck, it looked like a ship over empty water. Below, the system had to collect sediment, overcome enormous pressure, and manage thousands of meters of pipe without losing connection. Japan had discovered and mapped the mud years earlier. The breakthrough was proving that a connected recovery system could physically bring it up from this depth. This distinction matters. It was an engineering demonstration, not a commercial mine. There was no continuous industrial production, no competitive cost per kilogram, and no finished magnet emerging from the other end. But one theoretical step had become physical. The ocean was still hostile. The distance was no longer an absolute barrier. A successful test can last hours. An industry must operate repeatedly through storms, equipment wear, pipe stress, maintenance cycles, and abrasive sediment. Pumps must survive 6 kilometers below the surface. The ship must hold position while the ocean moves. Every interruption is expensive, and every processing step consumes energy, chemicals, space, or transport capacity. Japan's current development program runs from fiscal 2023 through 2027. Its goal is not merely to repeat the lift. It is to develop a connected chain of mining, lifting, concentration, separation, and refining. Earlier trials lifted seabed sediment from 2,470 meters. The 2026 operation entered a much more extreme environment. The next test is repetition. Recovering useful quantities consistently, not producing one symbolic batch for the cameras. Pre-concentrating the mud near the seabed could reduce the mass sent upward, but it would place more complex machinery in one of Earth's hardest places to inspect or repair. Every solution creates another engineering problem. And even if Japan solves continuous lifting, the most important bottleneck may remain above the water. Mud is not a magnet. Its valuable grains must first be concentrated and chemically separated into individual oxides. Those oxides must become purified metals, then alloys, then precisely manufactured magnets. This middle chain is technically difficult, chemically intensive, and expensive. It is also where China's dominance is strongest. Decades of production created specialized knowledge, trained workers, supplier networks, and economies of scale that one new machine cannot copy. If Japan lifts the mud but sends the concentrate into a China-centered refining system, it has moved the mine without removing the dependency. That is why this project is part of a wider strategy. Japan has backed Australia's Linus, heavy rare earth processing at Kermag in France, recycling, material efficiency, and strategic reserves. The seabed deposit could anchor this network, but to change the balance of power, Japan must connect the ocean operation to separation, metal production, and magnet manufacturing outside China. There is another test that cannot be measured only in dollars. The deep seabed contains ecosystems adapted to darkness, high pressure, cold, and extremely slow change. Many species and biological relationships around Minamitorishima remain poorly documented. Mining could disturb habitat directly. Sediment plumes could carry particles beyond the collection area. Machinery would introduce noise, light, and vibration. Waste handling raises another question. What material is returned, and where? Japan has conducted baseline surveys, long-term observations, autonomous underwater vehicle monitoring, and tests using international standards. Its closed, double-pipe lifting concept is designed to limit uncontrolled sediment release. These measures matter, but monitoring is not proof that industrial extraction is harmless. If the damage cannot be measured and contained, engineering success will not be enough. The environmental case must be built before, during, and long after larger demonstrations. So what does this actually change for China? One ship cannot replace a supply chain China spent decades building. A Japanese operation would begin smaller and probably cost more. But Japan does not need to replace all Chinese production for the project to matter. The strongest monopoly power comes from customers believing they have nowhere else to go. A credible emergency source changes that calculation. It could keep essential factories operating during a cutoff, support stockpiles, strengthen negotiations, and reduce the value of export controls as political leverage. Minamitorishima would work alongside recycled magnets, Australian feedstock, French processing, alternative motor designs, and new separation capacity. None is sufficient alone. Together, they create redundancy. China would still hold major advantages in cost, scale, expertise, and magnet production, but its control would become less absolute. In a strategic industry, the difference between total dependence and a difficult backup supply can matter more than the difference between cheap and expensive material. The honest scorecard is therefore divided in two. Japan has proven that the deposit exists and contains valuable rare earths. Researchers have modeled its scale. Laboratory processing shows that richer grains can be concentrated. And in February 2026, a connected system recovered rare earth-rich sediment from approximately 6,000 meters. Japan has not yet proven continuous production, equipment reliability, competitive cost, environmental acceptability, large-scale separation, refining, or magnet manufacturing. The project may never produce the world's cheapest rare earths. It may not need to. Governments pay for spare capacity, stockpiles, and defense systems because they remain available when ordinary markets fail. Minamitorishima could become economic insurance, expensive during normal trade, but indispensable during a crisis. From the surface, the Pacific around Chikyu still looks empty. The first recovered mud does not resemble a geopolitical breakthrough. There is no finished magnet, no new factory, and no guarantee of commercial success. But the important object is not the first container of sediment, it is the possibility of a second route. China still controls the rare earth system. Japan has not broken it, and commercial scale may take years. Yet a monopoly does not have to disappear to lose power. It only needs a credible alternative. And 6 kilometers below the Pacific, Japan may have found the first physical step toward building one.